The other day, I was listening to a CBC podcast. Honestly, you might have.
CBC podcast again?
Yeah.
Or is every intro of a CBC podcast?
No, but this time it is. Okay. And honestly, you might have listened to it. I don't remember which one it was, but some CBC thing.
Sure.
And it was talking about a murder that occurred 36 years ago.
Okay.
And someone was wrongfully convicted and did 10 years of prison.
Yep.
But the murder was discovered not long ago by using a genealogical database of someone in his family. But the murderer was dead 5 years ago. So that's kind of an interesting thing. But what jumped to me is that it's so creepy that we use one of those like 21andMe is the name?
Yeah. Is it?
Or and you?
But yeah, the DNA
Yeah.
like mapping tests
Yeah.
or like predisposition or whatever. Yeah.
Yeah, to find a murderer which didn't use those databases, but like someone in his family did use it.
Yeah. Yeah. It's true. There should be. I don't know if there is, but I could imagine that being regulated. I don't know. That you might have to disclose. You may not be forced to disclose. That's true. Like that family member incriminated this person, right?
Yeah. So like it's cool in the end that they found who it was, but it's kind of creepy.
But like, imagine if it wasn't like murder, if it was some controversial gray area instead.
Sure.
You know?
Yeah, and the fact that the police had access to that database is kind of awkward.
Oh, I was listening to another podcast. I don't know if it was CBC, but this was a while back. This was a few years ago, or a couple of years. I don't know. It was in the past, where a lot of Canadian police forces were using the facial recognition technology, but like independent, like police chiefs and stuff had no idea.
Oh.
It was just like investigators or something. Like they're just like, oh, well, we're at a dead end with this case. Why don't we just try to run it through this thing? And this company was giving out deals to police forces. Mm-hmm. But like when it was discovered that they were being used, they approached the like chief of police or whatever, and they're like, we have never used this before. And they're like, are you sure? Because like we have emails of like your employees using this thing. Yeah. And then they go check and they're like, okay, we may have used this before.
Yeah.
Like,
yeah. It's on my list of things to talk about in this podcast because I find I hate this subject.
Facial recognition technology, or
and like its use and abuse.
Ah, interesting. We could do like a intro to deep learning thing, like at the same time, right?
Oh, I need to harass one of my friends in machine learning. Okay, remind me to harass my friends.
Okay, great. I will.
All right.
You harass me every day already.
Welcome to a new episode of Randomly Typed. I'm JS.
Hi JS, I'm Lance.
Today, we're not talking about CBC. I want to talk about... I want to talk about lossless compression. I've been reading a book in the last, 2 weeks, 3 weeks, about image compression. But today we won't be talking about images, but we'll be talking about compression algorithm that doesn't lose data.
So lossless, yeah.
Lossless, yeah.
Because there also exists lossy. And you mentioned that we won't talk about image compression, but I know JPEG is lossy.
Yeah. So okay. So let's talk about lossless and lossy. Normally, lossless algorithms are generic. So you can pass pretty much any stream of data into it and you get back another stream. And you can do like the inverse operation to get back the exact stream at the beginning.
Yeah, so that's the definition, right? You can like apply it and unapply it.
Yeah.
And then get back the exact same thing. I guess when you say generic, it's sort of just like, I have no idea what this data might be used for, so we probably better preserve this.
Well, it's exactly that. It's like it's not domain specific. The thing with lossy compression is that it's domain specific. So you cannot use an algorithm for sound for images.
Yeah. Yeah, that's true.
Because the difference is that most of the time it uses human perception to know what you can drop so the user doesn't realize. For example, like in images, we know that our eyes are much better at seeing differences in light rather than colors. So you can drop more color before you can drop light, and we won't see the difference.
Yeah. Or I've also seen, like, if you have, geez, I have no idea if this applies, but I remember there were like repeated run compression algorithms or something, where instead of, like, let's say you had 100 red pixels to compress, like in its original format, you would do like red, 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 red 100 times. But of course, you can compress it to like 100 times red pixel. But the thing is, if you have an almost red orange pixel right in the middle, like you, without lossy compression, you would be forced to do like 49 red, one sort of orange, and then 50 red. But lossy lets you cut that out altogether.
Yeah, so you would like transform your almost red to red and just...
Yeah. And then, yeah, get the smallest size possible, right? So yeah, that's lossy.
Yes, so that's exactly what we're not talking about today.
Great. Now that we've talked all about it.
Yeah, so because I honestly think the lossy part is more complicated and there's more things to talk about, and I'm not ready. So I want to finish my book first.
Cool. Maybe the next one could be about lossy.
I'm not a
or the
fast reader.
next one.
Yeah, exactly. Yeah, and we already promised the two-factor thing.
Oh, that's true. I haven't even looked into that.
Yeah, me neither.
Okay. We'll figure that out.
Yeah,
it might not happen. We'll see.
Yeah. We don't keep our promises anyway.
No, we don't owe you anything.
It's our podcast. There's many different ways of compressing data losslessly. What would you say if in an exam I were to ask you, how would you compress some random string without knowing like this domain specific thing about that string?
That is a hard question because I'm probably going to get it wrong as I came totally unprepared. But the only thing I can think of is to, in any way, shape, or form, try to look for some kind of pattern so that can be compressed, really, that you can express in an alternative means that might be shorter. So if you had some binary and like you saw that every, like just by chance, every third bit was a 1, then you could find some way to express all the other bits and then express that that condition, that like predicate that every third bit must be a 1.
Mm-hmm. That's interesting. We won't go in algorithms that directly use that today. I don't know how easy it would be to generalize to any stream, but that's an interesting idea.
Yeah, no, definitely. And I'm sure it'd mostly be like the naive way I can think of doing this is just literally brute force. Just like try and find any combination that's nice, which is not great, obviously. So tell me more about how to actually do this now that we know the not great way.
All right. I put the algorithms in some sort of order that in my mind made sense. So bear with me. So the first part is dictionary coding.
Okay.
So normally a dictionary coding is substitution coder. And there's two like main variant here. So a static dictionary. For example, this is kind of domain specific, which is interesting in a lossless compression. So for example, for Brotli, which is like the new cool algorithm on the web, it comes with a 120 kilobyte dictionary for like all the time, like in the algorithm, not in the payload, of like normal known pattern in HTML, JavaScript, CSS.
Okay.
For example, this dictionary could contain like smaller HTML greater than, so like the opening tag for HTML. So like in Brotli, when you see that, you could say, don't write this, go see what's in the dictionary at the position like 300 or whatever, like a pointer to the dictionary.
Right. So I guess it's somewhat similar to what I was describing, where it has a pattern and finds a way to make it smaller.
Yeah, it's a known in advance dictionary.
Yep.
So the other one is dynamic. So you build your dictionary as you go. So this has the advantage of being less domain specific, but you always need to send your dictionary. So you lose kind of the gain you would get with static dictionary.
Yeah, so you're saying that like with static, it's known in advance on both the compression and decompression sides, so you just don't even need to bother including it. Whereas dynamic, I assume when you compress it, there's a part of the compressed blob that contains the dictionary that was used to compress that thing.
So, okay, let's go with Lempel-Ziv, which is probably one of the most influential paper or algorithm. It was initially published in 1977. Sometime you will see like LZ77. So that's for the publication in 1977. And this algorithm uses a dynamic dictionary coding. So imagine you have a stream and you keep a moving window of the stream. Let's say you have 200 bytes. So let's use characters because it's just easier to talk about, right? So you have 200 characters in your input string that you want to compress. Let's say you keep a window of, 20 characters before where you're right now. So you would go to the first character, look at 20 things before. Did I already see this pattern? Yes, no. And you do this. And as soon as you see a pattern you already seen in the past, like 20 characters, because you kept a window of 20, you would say, rather than putting this pattern, and this pattern could be like 10 characters, like hello, or hello is not 10, but
hello.
Yeah, exactly, right? So you would say like, go back like 12 characters in the past and take 10 characters from there.
Yep.
So it's like two variables. How far back and how much.
I'm 100% following.
So that's LZ77, which is the base of so many algorithms.
That's pretty nuts, though, to think that, like, I mean, it must work. Like, it must work decently well.
Oh, yeah. Super well.
It's crazy to think that there's that much non-entropy.
What do you mean?
In that, like, I don't know. I sort of imagine a stream of, like, random bytes.
One good way to know if you have a good random stream is that if you can compress it, it's not random. Normally, like some good random thing, you cannot compress it.
That's true. Yeah, it makes sense. Pretty cool. Never thought of it that way.
Do you see a problem with LZ77?
Should I see one?
Yes.
Well, other than you need to... a problem how? Like a problem with what?
What could be improved?
Okay. So the only thing I can think of might not be at all what you're looking for. But all I can think of is that like your window is like fixed and you might be looking at the wrong granularity.
Exactly. That's the exact problem.
Yes. Beautiful.
So LZ78. So a paper or an algorithm they released the year after was trying to fix that problem. So the problem here is that you need to optimize one parameter, which is the window size. So if you put something too big, your algorithm will be slow. And if you take something too small, your algorithm won't be as good as it could be.
Yep.
I won't go into the details because it was kind of weird and more visual. But so what LZ78 did is that it's building a dictionary as it goes. The window is like the whole stream with some fancy algorithm and how they're building a binary tree. And how you can like use
that makes
a part of the tree.
Perfect sense to me. And that like a window of 10 characters is also a window, 2 windows of 5 characters.
Yes.
Beautiful. I love it.
Here, one of the problem is that it's a 2-step algorithm where LZ77 was a 1-pass algorithm.
I can also imagine your dictionary getting much bigger in this case. Oh, well, no, I guess not necessarily because, sorry, that's not true. That's a lie. Your dictionary would not be bigger, but I guess the amount of memory needed at runtime would be much bigger to hold this tree in memory.
Yes, but I know there was optimization to like shove them down to like arrays rather than keeping it in a tree.
Yeah, of course, yeah.
Yeah,
but
sense. The thing with LZ77 is that when you send the compressed stream, there's no dictionary at the beginning because like the stream is a dictionary itself. which LZ78 is not.
Cool.
Cool. All right. Another variant. LZSS for Lempel-Ziv Storer Szymanski. I'm sorry for that name I'm destroying.
I wonder if Storer Szymanski just like discovered an improvement off of LZ and wanted to like ride on the LZ wave.
Honestly, yes.
Yeah.
Exactly that.
But also, it also makes it seem like they had something to do with the original algorithm, which it might be slightly misleading. But
so it's pretty much LZ77, but with some tweaks. But the interesting one, in my opinion, is that it's super simple. You only do like the pointer if your pointer is smaller than what it's pointing to.
Oh, makes sense. That also makes a lot of sense. Yeah.
So the advantage of LZSS is that you cannot create a bigger output file.
Yeah, that's true. That's a good constraint, right? It's impossible to do so.
Yeah, which LZ77 could do.
Yep.
And 78 too, I guess.
It seems like it, yeah.
Yeah.
Oh, that's great. That's a good constraint to have. And I love this progression of like, in quotes, like I say obvious, like seemingly obvious improvements, like small little improvements over the original. Yeah.
So there's so many variants of LZ. And obviously I won't go through all of them, but it's pretty interesting. Like some are like big changes and some are small changes.
Cool.
All right. Let's go to the next big influential way of compressing data. Do you know about Huffman coding?
Never heard of it before.
Oh, really?
Never heard of this.
Interesting. So it was published in 1952.
Wow.
Earlier.
Well, I mean, okay, I was going to say in computer terms, this is old. But I guess in like, I don't know, but crypto's been around for a long time too, right? So.
Sure. But 1952 is like, what, 10 years after World War II? So still...
Give or take a few years.
Yeah, exactly. Yeah, and it was published in a paper called A Method for the Construction of Minimum Redundancy Code. I just like the name.
Yeah.
There's multiple implementation and improvement as everything, but the normal or like initial way was a multi-step algorithm, which LZ77 was not. Huffman coding is using variable length coding table. So this means that they can use different size of like pointers or things that are compressed. So for example, in LZ77, it was always like 2 integers, or how big was your pointer. But here, they're taking the data that we see the most often, and we translate it to smaller output. That's the trick. Everything you see more often will be compressed to smaller things.
So, but this is like dynamic too. Like it analyzes the stream.
Yes.
And then figures out what is seen most often, and then places the thing that's seen most often in the smallest pointer possible.
Yes. But here we're not using pointers. We're like using code symbols.
I say, sure, yeah.
But smaller representation.
Character.
It's exactly what you said. It's a 2-pass. First, you go through all your stream, look for repetitions. Let's say characters. The character that you see the most often is at the top of your list. And you put the output result, the smallest thing you can represent. Mm-hmm. And the one you see the least, you put it the biggest output thing. Yeah. So this means, contrary to LZ77, everything is transformed.
Yeah, that's pretty cool.
Because like for LZ77, if your stream was like perfect randomness, you would get back probably the input stream as an output stream.
Yeah. I'm sure there's a way of doing this as an infinite stream too. But you just like buffer every 1,000 characters do this, right?
Exactly. So this one is using dictionary coding again. So this means that you need to send the dictionary that you've built in the first pass.
Yep.
Let's use the example from the Wikipedia page, which is encoding the string. This is an example of a Huffman tree. So that's the input data. If you were to encode this in like a 8-bit string, like 8-bit character string, it would be 288 bits.
Okay.
And once it's encoded, it's only 135. There's a good gain, right?
Yeah, like 50%.
Yeah, exactly. First pass, you go through every characters and you give them a frequency. Here in an example, like the space character is there 7 times, A 4 times, E 4 times, F 3 times. So this means that the smallest output character we can use, for example, is a 3-bit output. In our example, it is 111.
Why 3-bit though?
Because you need output characters that you can distinguish, like that if you see them like one after the others, you can cut them without...
Like they need to be recognizable and distinguished from adjacent characters?
Exactly, because if you were to use 1-bit output characters, you couldn't know where to cut your characters.
Yeah. 3 seems strange though.
Is the smallest, as far as I understand. But so we have three characters. Sorry, 3-byte output. We can use 111, 010, and 000. So this means that space A and E gets a 3-bit output character, and F gets a 4 bit, sorry. So 1101, and at L, which has a frequency of 1, we jump to 5-bit encoding.
Yeah. Okay, this makes sense to me. It reminds me of like tokenizing, where you need to end up in a final state which is a token, right?
Yeah. So like the second pass is you go through your string, and for every character, you go see in your table and you take the output character and you put it like in your output buffer. And for the decoding, it's the inverse, right? You look at the table and you look at what you have and you get the output character.
This would be a fun side project for anyone listening.
Honestly, I'm like with modern languages, I'm sure it's like 100 lines of code.
Yeah, yeah.
Like it's super simple. That's what I love about those algorithms. Like the base algorithms are super elegant and easy to do and easy to understand.
Agreed. Yeah.
All right. Do you want one that is really not easy to understand?
Do I?
It's called arithmetic coding.
Okay.
So I'm already sorry because this one is kind of hard to
talk
about.
Sure.
So it's really visual. Honestly, you should go take a look when you have some time, but I'll try to give you a good example.
Okay.
It's a really different way of seeing a way to encode data than the two ones we looked at before. The trick here, like there's air quotes, is to encode your whole data between 0 and 1.
Like as decimals?
Yes. What problem do you see, Lance?
Well, significant digits is 1.
What do you mean?
In that, like a floating point, you need to specify. In this case, you need to specify how many sig figs you have.
Yeah.
Because otherwise, you would never know when to stop. But
yeah, because our hardware are normally like using 64-bit float numbers, right?
Yeah.
So this means that as long as you can do your thing with a 64-bit float, everything's like blazing fast.
Yeah, it makes sense. Okay, yeah.
But as soon as you need bigger numbers, because you're starting to lose precision, your algorithm becomes way slower. So this means that, honestly, it's not a feasible way of doing compression, but it's an interesting one.
I guess unless you're compressing really small things, but then what's the point of compressing if they're really small?
Well, I'm sure there's some use case.
Yeah.
But yeah, so it depends on how your hardware is able to manage those small numbers.
Makes sense.
So let's go through the example from the website gocompression.github.io. That's a good website. It's a fun, quick website talking about compression. Here they're compressing the string hello, so HELLO. Albeit like the previous one, we do a frequency table, H1, E1, L2, O1. And here, the third column is the probability. So it's 20%, 20%, 30%, 20%.
Okay.
And the trick is to give bigger range for the thing that occur more often. What you do is you take your space between 0 and 1 and you split it for every possible letters. Between 0 and 0.2, so like the probability 20%, you get H. Between 0.2 and 0.4, you get E. So another 20%. Between 0.4 and 0.8, you get a L. So like the 40%. And between 0.8 and 1, you get O. Now you have between 0 and 1, the 4 possible letters. The first step is to take your first letter in your string, which is in our case H, and you go in the range that was given to H. So in our case, it's between 0 and 0.2.
Mm-hmm.
And now just imagine that we are zooming in that range. So now like your 0.2 becomes like your whole state.
Yep.
And now you do the same split, like 20%, 20%, 40%, 20%, but between 0 and 0.2. So now you get the numbers 0, 0.04, 0.08, 0.16, and 0.2.
Okay.
And and again, now you take your next letter, which in our case is E. We go between 0.4 and 0.8, and you zoom again and you do it until you encoded your whole string.
Okay.
At the end, what we get is that the string hello is between the numbers 0.06368 and 0.06496. So it gives us a range where the string is.
Right. So I guess if you provide any number
Exactly.
within that range, along with your dictionary, you can retrace your word.
Yeah, exactly.
Beautiful. I love it.
If you have a static dictionary, which you could, you would only need to send one number.
Yep.
And if your dictionary is dynamic, well, you need to send the dictionary and the string. The number.
That is incredibly clever. I wonder, there's got to be a way to represent this and circumvent the floating point issue.
Yes, well, we have algorithms for dynamic, what's the name? Arbitrary precision numbers, but they're slow because it's all done in software.
Right. No, for sure. But I mean, all these other compression algorithms are also done in software.
Yes, but I guess arithmetic on floats are really slow.
So that's sort of what I was saying. Like, there must be a way to translate this into like bits of some sort, and like or them, or
I see what you're saying.
Like do some weird bit shifting and achieve the same result. I'm convinced I'm gonna do this as a side project legitimately.
You should go read on the subject, because honestly there's like all the other algorithms, there's many like derivatives and improvements, and I'm sure there's ways of doing this, but it's not the most easy one, let's say.
Yeah, for sure.
So there you go. Arithmetic coding.
This has been super fun.
This one is super weird. Like I'll just put air quote here again. It's like the only one I couldn't think about by myself, because it's like all the other ones make sense to me, but this one's just like crazy.
Well, it's definitely outside the box, right? Like,
The next part I wanted to talk about is like how we use compression on the web. It's no new algorithm. Just let's chit chat about the web. All the next algorithms are like just a mismatch of what we've seen.
Okay.
So even the new cool things like Broadly is like using LZ77 with some Huffman coding and second order context modeling plus a dictionary. So it's using things that already exist.
Yep.
Normally when we send and receive data on the internet, we receive like compressed payload. And the normal compression algorithm we can see is gzip, compress, and deflate. Gzip is using LZ77 again with CRC 32-bit at the end or the beginning, not sure, just to validate that you didn't corrupt the data. Compress is using LZW this time, which is Lempel-Ziv Welch, which is an improvement over LZ78, which is using some Huffman coding. And finally, deflate is a variant of LZ77, again with some Huffman coding.
Of course. This reminds me so much of that. I think it's Tom search. Is that right?
What is it?
Give me a second. Sorry. I said search. I meant sort. No, okay. This is what it is. The Tim sort.
What is it?
So it's exactly this. where it is a sorting algorithm that is either partly merge sort and partly insertion sort, depending on decided based on just like empirical usage in the real world, where
Right.
it's just like it'll do one or the other depending on a circumstance. Where these optimizations are trying to be smart about like what it's mostly used for, I guess.
Those three algorithms have been used on the web since pretty much the web. And most of the time we were seeing gzip, which was giving some good results.
Yeah.
But in the last 5 years, so in 2015, Google released the Brotli compression algorithm, which is, like I said earlier, it's again using LZ77, Huffman coding, and a dictionary. But now it's getting something like maybe, let's say, at least 15% improvement over gzip.
Wow.
Yeah. So this means
that's awesome.
Yeah. So since 2015, we compressed more data, which we couldn't before. So this means less data on the wire, faster internet, I guess.
Great for everyone.
Yeah. So I've been looking at the report from the HTTP archive from 2019. And currently, okay, get this, 72.87% of the traffic is not compressed.
This does not surprise me in the least bit.
That's crazy.
Every time I've ever set up like an Nginx reverse proxy or something, like you'll always find those like tutorials of like checklists to do when setting up reverse proxy, and gzip is like compressing is always in there of like most people just don't do this, right? Because like it usually doesn't come out of the box.
Yeah, but that's crazy. It's like most of the textual traffic could be compressed, but it's not.
Yeah.
Yeah, and afterward, like 30% gzip and like 7% for Brotli.
Wow, that's 7% is still quite a bit.
It's quite a bit, but it's really better like in pretty much every scenario. But I guess it's too new and people don't care.
Yeah, but I mean, for 7% adoption on the web after only 5 years is quite impressive. Like IPv6 took what, like 30 years, and we're not even there yet?
I think last year it was its 20th birthday or something like that.
Exactly, yeah. So this is, by comparison, this is a much better adoption rate.
Yeah. I feel like you have a good reason to do good compression. It's just like you pay less money. Like it's free money.
Yeah, but I know a common argument is that passes the burden onto the users of your platform or your clients, and that like their CPU and their energy bill goes up.
But normally compression are pretty easy to decompress.
Yeah.
Like most of the algorithms we've seen today are pretty straightforward to decompress, and it will be less effective to actually not compress. Like it's easier to receive the data and uncompress it than not doing it.
I was going to say like it would be pretty cool to do like an energy efficiency study of these compression algorithms.
Yeah. That's an interesting question, and I don't have an answer for you.
We'll see if I have the motivation to do this for the intro of the next episode.
I'll buy you what it's called, energy meter for your computer.
Yeah, I'll just look at my hydro bill.
Yeah, let your computer run for 1 month.
Nobody turn on the lights.
All right, that's what I had for this episode.
Well, thank you so much. This was really, really fun.
Yeah, I tried to like copy your style of episodes because when I looked at our listening numbers, like people listening to our podcast, I realized that all your podcasts are much more listened to. So I guess I should go for more algorithm.
Well, it's nothing to say about you. I'm sure it's just that
my subjects
matter.
are boring, right?
I guess people like theoretical stuff. I don't know. Write into us and let us know if you're listening. If you want to hear about more theory or not.
Yeah, we're asking our mothers and that one guy that sent us an email. We love you.
Hey, we have like what 30 listeners approximately.
No, not even close.
Just wishful thinking.
Yeah, really. Though, you know something cool? We are at 924 total play. So we're soon reaching 1,000.
That's great. Yeah.
Whatever this means.
Yeah, exactly. 1,000 plays from us. I'm sure. Are we in the double digits on YouTube?
No, there's no one.
By the way, we release all these things on YouTube too.
Yeah.
If
No,
ever
there's
you wanna
actually
subscribe
one
to it.
person watching on YouTube.
Like right now?
No, I know, like all
What do you mean?
all the videos have like one.
Oh yeah, it doesn't surprise me. We really got to market this thing, man.
So I know who you are, YouTube person.
Oh, only 3 subscribers. This has got to be at least double digits. Then we'll make the money will start rolling in.
Oh, God. Okay, Lance. I give you a task. Create a Twitter account and manage it.
One day I'll find the motivation to manage my own Twitter account, and then I'll consider this.
Yeah. I don't like really social media, so I guess we won't ever do Twitter accounts.
Me neither. I've got them all, but I don't participate. I'm just a phantom.
Yeah. All right.
Cool. Thank you so much, Jess. This was fun.
That was fun. See you in, I don't know, 2 weeks or more if we don't write an episode.
We'll figure something out, I'm sure.
Yeah. All right. Thank you.
All right. See ya. Bye.
This podcast is both free and free, as it's distributed under the Creative Commons.
You can contact us and find show notes on our website, randomlytyped.com.
The intro music is by Vansky.
Thank you, Vensky.
And thank you, listener, for indulging us.